Okay, welcome back for the final part of our lecture where we talk now about dynamic models. So before, actually, what we did is that we looked only at so-called static models. That means that the outcome variable y only appears on the left-hand side and there was no y on the right-hand side. So of course, we could use x variables and those could be lagged. So you can have a model where y depends on previous x's or even future x's. These kind of things are all allowed. What we will, however, see is that once you put lags of y also on the right-hand side of the model, this can give you trouble and you will have to use a little bit of a different treatment. Okay, so let's take a look at this. So as I said, we talk about dynamic models when we have YIT on the left-hand side, and we have, for instance, like previous Ys on the right-hand side. Now, in general, we can actually allow for other control variables. And in fact, in one of the most famous papers in this literature by Manuel Arellano and Stephen Bond, which we'll discuss at the end, they look, for instance, at the unemployment rate, YIT, which depends on previous unemployment and some control variables. Now, the control variables, they're of course important in practice. However, they're not really important in order to see what are the issues of dynamics. So what we will do in the following is that we assume that this beta here is simply 0. So there is no other x variables. So we only care about this type of model here. Very simple. YIT, the only explanatory variable is the lag of YIT. And we have a fixed effect here. And thus we call this an autoregressive model of order 1 because there's only one leg with fixed effects. Of course, like you can put a second leg, then it would be an AR2 model and so on and so forth. Many of you took time series courses, and for you, this is probably boring stuff. You know all this already. Okay, now we want to investigate this still from the micropanel perspective. So that means that n goes to infinity and t is still small. So t is going to be fixed in our treatment here. Okay, so let's see what happens if we simply use the same ideas that we used in GMM before. So let's assume strict exogeneity, which in the dynamic model simply means, well, the expectation of u, the conditional on the time series of all explanatory variables and alpha is 0. And of course here, the only explanatory variables are the lags of y. So that's what you see here. It starts with yi0, which is often called the initial condition. And it takes all time series, like both past and future y's. Now, we will assume in the following that yi0 is actually unobserved. So yi1 is the first observed data point. So that you have to check when you look in books. Some people kind of assume this is observed. We assume it's not observed and yi1 is observed. So that's a little bit of notation where you have to be careful when you look in the literature. Okay, let's see. Does strict exogeneity work? Well, and it turns out, no, it's too strong. It leads to logical contradictions. So, for instance, like strict exogeneity implies that you have contemporaneous uncorrelatedness. So you have UIT and YIT are uncorrelated. And now if you look at this, well, you simply plug in the model for Y. So here we are, right? So if you replace YIT with this model and you just open the brackets, then you would see, well, this term non-problematic because by this assumption here, it would be 0. This assumption also not problematic because again, strict exogeneity implies it's 0. However, this here is actually the variance of the model error, and the variance of a random variable is always positive. So this can only be 0 if it's not a random variable. If it's a constant, then the variance would be 0. However, in our models, the u is always a random variable, and therefore the variance is larger than 0. Okay, so that means this assumption implies this, but our model says this. So both cannot go together. So strict exogeneity is too strong, and therefore we need an alternative. And the alternative that is mostly used is this sequential exogeneity assumption, where the difference is that now we let ut be uncorrelated with all the legs of y and up to the y from the previous period. Yeah, so we don't have contemporaneous y's here and we don't have future y's. Okay. Yeah, so, and because of that, there is no logical contradiction using the sequential exogeneity. Okay, now the next thing is we have an assumption. Let's try to see whether our kind of previous estimators still work. So let's simply try the first difference estimator in order to estimate the parameter rho, which is a scalar. It's only a one-dimensional parameter that we want to estimate in this model. Okay, let's do first differencing. So here yit, delta yit is simply yit minus 1, business as usual. And because, yeah, so yit minus 1, so let's say t is 3, then yit minus 1 is 2, and delta yit minus 1 contains yi1, which is the first observation. Yeah, so you see that we have to start at 3, because if we were to start at 2, then we would have, because, you know, delta yi1 contains yi0, and that is not observed. So this is why we need to start at 3. Okay, so let's look at consistency of the first difference estimator. Now, because first, like yit is a scalar, we don't have this yit prime thing. No, we just have the square. Easy peasy. Okay, now, of course, we know this thing, if n goes to infinity, will converge to some expectation. And because this is a random variable, we know that this will be positive. Yeah? So the expectation of the square of this random variable will be something positive. So the inverse here is defined. Now, the interesting part is, of course, what happens on the right-hand side. There, we just employ the usual idea. So we have here the delta yit, and the delta yit can be simply again replaced with the right-hand side of the model. What we then see is that the first part is again yit minus 1 squared, so the rho comes out. So this is really business as usual, as we've seen it many times before. And then we get the following expression where we now have the delta uit here. Okay, as I said before, the first part here, non-problematic. Yeah, so that's okay. The inverse exists, no problem here. Now the problem may arise in the second term. So the rho hat will be consistent only if like the sum of these expectations will be 0. Now, is that the case under sequential exogeneity? Let's find out. So here we simply replace delta yit by, well, yit minus, so delta yit minus 1 is replaced by yit minus 1 minus yit minus 2 in brackets. The same idea for the delta uit. And then you open the brackets. And you see that here we have yit minus 1 uit. This is earlier than this. Okay, 0. Now, this y is earlier than this, also 0. Now here, this is a problematic term. This and this are from the same time period. And this, oh no, this is actually unproblematic. Okay, wonderful. So here we have a problematic term. Yeah, so this is 0, but this is non-zero, and therefore, in general, our first difference estimator will not converge to the true rho. So, okay. So sequential exogeneity is not enough to employ the first difference estimator directly. And in fact, like another super famous paper, Stephen Nickel has shown that, also Econometrica, I think, has shown that in fact the bias of the first difference estimator is again of order 1 over t. So which means that if you have a short panel, let's say 5 time periods, big bias. If you have a long panel, let's say t is bigger than 20, small bias. So the first difference estimator actually works if the time series dimension is large enough. Yeah. Okay. Good. So we have a biased estimator, and let's say we have a short panel. That sucks, no? Right? Our estimator that we want to use doesn't work, has a huge bias. So we need an alternative. And a very nice and clever alternative is actually IV estimation in dynamic models. So let's see. Um, okay, so sequential exogeneity implies, so let's look again, this is our problematic term, right? The UIT minus 1 here. UIT minus 1 is uncorrelated with all the y's up to t minus 2. And this, of course, by the law of iterated expectation, also UIT, so without the minus 1, is also uncorrelated with, or like, the condition expectation is also 0, which you can see by using the law of iterated expectations, meaning that the smallest information wins. You see that here we condition on a larger set, and on the outside we condition on the smaller information set. And this is the same thing as conditioning on the smaller information set. So this is sometimes called the smallest information wins. Yeah, okay, so and you see that when I condition on the larger set here in the middle, this is 0 by our sequential exogeneity assumption, and therefore the whole thing is 0. So by sequential exogeneity, we know that our delta UIT will actually, so this the model error after first differencing will be uncorrelated with all the legs of y's up to t minus 2. And this is something that we will now exploit. So that's exactly what I just said. So we have a couple of moment conditions because the delta UIT is uncorrelated with legs of y that are sufficiently far away from the period t. Okay. Yeah, so of course you can make use of these moment conditions in different ways. So for instance, there's a famous estimator by Anders and Zhao who simply use delta YIT minus 2, so this thing here, or just YIT minus 2. With or without the delta, both times it's okay. So both are valid instruments, and you instrument the endogenous delta YIT minus 1. Yeah, so delta YIT minus 1 is not uncorrelated with delta UIT. So you use this thing here as an instrument for this. Okay, now we have already checked that this is a valid instrument. It's uncorrelated with the model error with delta UIT. But why is it actually relevant? Well, I mean, the relevance, that's the magic here of the dynamic model. The relevance follows immediately whenever we say that our model is correctly specified. Yeah, so because of our model, we can get internal instruments. Yeah, so so pretty much if you look at our first difference model, and you look at delta YIT minus 1, then you see that it actually depends on delta YIT minus 2 if rho is non-zero. And if rho is non-zero, you know already that there will be some correlation between delta YIT minus 2 and delta YIT minus 1. It just comes directly from the model. So this is what I want to say here. So there is some correlation as long as this rho parameter is non-zero. Okay, so that's an internal instrument. We don't even have to look for any clever instruments. So we have this here for all t from 3 to capital T. So we pool those moment conditions. Yeah, so this is our moment function. And well, you see that the dimension of GI is simply 1 because we again use this pooling here. And that's the same as the dimension of rho. So rho is just identified. And then the GMM estimator is simply the IV estimator. And here we go. Yeah, so that's a very simple idea. It's a very actually kind of clever, and it works pretty well. Okay. Of course, this thing will be consistent because this is uncorrelated with delta UIT. Yeah, that is what we've just shown. So this thing will be consistent. However, we have more moment conditions available, and more moment conditions typically means more information, that means more efficiency, that means smaller variance, that means better inference. So we want this. And there is like an incredibly famous paper by Manuel Arellano, who is one of the most famous econometricians still alive, and Stephen Bond, who is also a pretty big name. They use all available moment conditions that are implied by 7 here. And if you look at their paper in the Review of Economic Studies, that has more than 30,000 citations, and that's absolutely insane. So most papers have maybe 1 citations. So like the average economics paper is not really read that often and cited even less. And their paper has more than 30,000 citations, which is absolutely crazy. Okay. So let's look at the moment conditions. We know that the delta UAT is uncorrelated with all the legs of the y's that are at least 2 time periods away. So for t equal to 3, we get 1 moment condition. For t equal to 4, we know that yi2 and yi1 are both at least 2 time periods away, so we get 2 moment conditions. And if we continue like that, then for the last time period, we have actually t minus 2 moment conditions. So what is the total amount of moment conditions that we get? Well, it is like 1 plus 2 plus and so on plus t minus 2. And this, by the Gauss formula, is simply t minus 1 times t minus 2 divided by 2. And what you see here is that the number of moment conditions increases quadratically in the number of available time periods. Yeah? So you get pretty quickly a huge amount of moment conditions. And so how would we write this in GMM form? We would have to make this huge matrix here. So MAB is now this number here, t minus 1 times t minus 2 divided by 2. And yeah, so we define a couple of normal stacked vectors. So one is starting at delta y3 goes to t. And this one here would be kind of the leg of this. Yeah, so it goes like 1 time period less. And then we can write our moment condition like this. Yeah, so this huge matrix times this minus rho times its leg. This would be 0 by sequential exogeneity. And as long as t is larger than 3, then of course rho would be over-identified and we would have to apply two-step optimal GMM. Yeah, so, and there it's again business as usual. We want a preliminary estimator that we can simply do by running this first stage regression. With that preliminary estimator, we estimate the optimal weight matrix, and then in the second step, we again run this minimization, and where this is now included, that's the difference to the previous version, and we get the estimator. And now finally, because gn of beta is a linear function, we can actually derive an explicit expression for rho AB. So we can solve this explicitly. And this looks a little bit messy, maybe. So we take the derivative of g. That looks like this, comes straight from this expression here. We also know what gn looks like, and therefore you see this pretty messy stuff here is the Arellano-Bond estimator. Super famous, beyond famous, more than 30,000 citations famous, which is crazy. Anyway, there are some problems. Like this Arellano-Bond is incredibly popular, as I'm not getting tired to stress, but actually it can work pretty badly. It's actually not that great. So for instance, if rho is relatively small, like it's close to 0, then of course legs of y that are far away from the current time period will only be very weak instruments. And in the last tutorial, we discussed what that means. That means your standard errors will be blown off and your estimator performs very badly, actually. Moreover, in applications, you should make sure that the individual dimension is much larger than the time series dimension. Because in the following paper, Arellano himself It's again an Econometrica paper, so he's really good. He shows that if you let n and t go to infinity, so that n and t grow at the same rate, then this estimator, this super famous estimator, actually becomes inconsistent. And yeah, one of the problems is that you have simply too many moment conditions. So like the number of moment conditions increases quadratically in t, and then for each of the moment conditions, you have just very few observations if n is not large enough. And therefore, well, the performance can be pretty bad. And can actually be shown that like the Anderson-Zhao estimator, which only uses one leg, can clearly outperform the famous Ariano bond estimator if t is relatively large. And there's also still some research going on about that. So for instance, Rootman here proposes to simply collapse some of the moment conditions. Yeah, let's not take them all. Let's just take a sufficient amount to have efficiency. But yeah, let's get rid of this problem that t, like the moment conditions grow as a quadratic in t. Okay, that was a quick run through of dynamic models. I hope it was more or less clear. Otherwise, well, we have next tutorial to discuss any questions that you might have. Okay, see you then.